Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Integration by Substitution. And please, as always, I encourage you to be an active learner as you watch this video. By way of introduction, once upon a time in your algebra class you were faced with solving 2 times the quantity 3x plus 5 whole squared minus 7 times the quantity 3x plus 5 plus 6 equal to 0. And this is complicated to solve, and the way you probably talked about solving it, we said, was let u equal 3x plus 5. And then I'll rewrite this. Everywhere I find a 3x plus 5, I will put a u. So this is 2u squared minus 7u plus 6 is equal to 0. And I can factor this in this way. So I have two factors multiplied together equaling 0. So in turn I set each factor equal to 0. And I conclude that u is equal to 3/2 or u is equal to 2. Those are the two solutions to this equation. Now the original equation though asks you to find out what x was, so we have to reverse the substitution. So I take the 3/2 and I say, oh, that was 3x plus 5, and I solve to conclude that x is minus 7 over 6. And when u is 2, that is 3x plus 5 is equal to 2, and x is equal to minus 1. So you see we solved this by using a substitution, but had to reverse the substitution. The same thing is going to be true when we integrate using substitution. We'll have an indefinite integral of f of x dx. And we will decide we're going to let u be something, and u will be a function of x. But also what will happen is, you see, we can't do this integral. The reason we can do this integral is we have x here and dx here. We can do this integral because we have u here and du here. Those must match. So we not only have to be concerned about the relationship between u and x, we also have to be concerned about the relationship between du and dx. That's probably enough integration. The best thing is to do a series of problems. And as we do these series of problems, we'll see that these equations are true as long as we have a function of u and du, a function of u and du, a function of u and du. So many of the integral formulas that we've discussed before are true as long as these match. Now for the examples. And since we are going to have to be concerned about, if we define u to be something, how do we find du? That's what we're going to do in these first 4 examples. And I know it's saying find dy, but we're going to be finding later du, but here we're calling it dy. So suppose y is equal to x cubed. And I know we did this before in the chapter on differentials. So if y is equal to this, we know that dy dx is equal to f prime of x, and that's going to be 3x squared. So dy is equal to f prime of x times dx. You could think about it as just multiplying by this dx, although it's actually something a little bit different than that, but you can probably get away with that most of the time. And so dy is going to be the derivative times dx. So this is 3x squared dx. In b, we have y is equal to x to the 2/3. So again, dy dx is going to be 2/3 x to the minus 1/3. Note that even though we're integrating, we're having to do derivatives as well. We're doing both things in the same problem. So we have dy is 2/3 x to the minus 1/3. But that means that dy is f prime of x, what we had up here, times dx. So that's going to be 2/3 x to the minus 1/3 dx. Again, with example C, y is equal to the natural logarithm of x. So the derivative is going to be 1 over x. So dy, in this case, is going to be 1 over x times dx. In the last example, if we have e to the x squared, so y is equal to e to the x squared, then dy is equal to e to the x squared times 2x by the chain rule, and then times dx. These are important examples because we're going to be using these as core parts of problems that we do later. So in effect, we've applied the chain rule in reverse. And this procedure is referred to as substitution or a change of variable. Now we can check our results, as always, by differentiating the answer. And while this doesn't mean you can do any integral, many integrals can be done this way, and this is a core thing that you're going to be assessed on. So when using substitution, we choose what u represents so that we obtain an equivalent integral in which the original variables, using x and dx, no longer appear, and which is more easily solved, and then we have u and du perhaps. But the answer, if it's an indefinite integral, you have to return to the native variable x. Again, some examples will help with this. So here's an example. You're to evaluate this integral here. The indefinite integral of 3x squared times the whole of x cubed plus 1 raised to the 10th dx. Now one could do algebra and expand this, but that would be a very long task to do this. So what we do is we're going to do a u substitution. And so the u is going to be x cubed plus 1. And if u is x cubed plus 1, then du is going to be 3x squared dx. Make sure you understand this step. So then we go back to the problem, and you see we have u raised to the 10th power. And 3x squared dx is, in fact, our du. Sometimes it's not this easy, but sometimes it is. So you see, you have u here, so I can apply our rule. Add 1 to the exponent, divide by the new exponent, and add a constant of integration. And then I have to reverse the substitution, going back to what x, our variable of x. So the answer to this problem is 1 over 11 x cubed plus 1 whole to the 11th plus c. And here's a check by differentiation. And what that means is if we differentiate this side, we should get the integrand. And you can see that we do. Here's another example. We're supposed to evaluate the indefinite integral of 2x dx over 1 plus x squared. In this one, we're going to choose u to be 1 plus x squared. And if we choose u to be 1 plus x squared, then du is equal to 2x dx. So when we look over here, then this top is actually just du, and the bottom is u. That matches, so we're integrating du over u, which is the natural logarithm of u. And we don't have to worry about the absolute value here because 1 plus x squared is always positive, plus c. But then we have to reverse our substitution, and so we put the 1 plus x squared in there, plus c. And that is the answer to this problem. Now you might say, well, suppose I try something and it doesn't work. That means you didn't make magic happen and you have to go back to the drawing board. That's why doing homework in this section is extremely important. Here's a different problem. We're to evaluate the indefinite integral of 2x dx over 1 plus x squared, the whole of that, to the 5 in the denominator. So what we're going to note is that, and we're just observing this, and you might think about where this comes from. This is some of the thought process. When I look at this problem, I say, oh, if I let u be 1 plus x squared, then du is sitting right there, or something close to du is sitting there. So our choice in this case is going to be u is equal to 1 plus x squared. And that means that du is going to be 2x dx. We go back to our original equation, substitute, and we get du over u to the 5. Now that is integrating u to the minus 5 du. And you see the u matches, so we can do this integral. And in fact, that's another measure of magic happening with your substitution because you don't have any other variables sitting here. Now I do this integral. You add 1 to the exponent and divide by the new exponent. So when I add 1 to minus 5, I get minus 4 over minus 4, and I can factor that out, and I can write u to the minus 4 as a 4 in the denominator. And then I can reverse my substitution, and everywhere there's a u, I put 1 plus x squared, And this is the final answer to example 4. Here's example 5, and some of these are getting a little bit more complicated. We're to evaluate the indefinite integral of, now this is the natural logarithm of 3x dx over x. And we're restricting x to be greater than 0 here for reasons that are sort of technical, and let's just not dwell on that right now. So what we're going to do in this case is we're going to let u equal the natural logarithm of 3x. Now we take when the derivative of this is going to be 1 over 3x times 3, so those are going to cancel. And so that's what we're going to get, is 1 over x is what the derivative of that's going to be. So this is how we handle the differentials. This is our substitution. So we go back to the problem, and you see that the red part is u, and the blue part is du. Again, we've got u du. So this is going to be, add 1 to the exponent, divide by the new exponent, is u squared over 2 plus c. But then we reverse our substitution, and u was the natural logarithm of 3x. So this is the natural logarithm of 3x whole squared over 2 plus c. Let's do another example. Here, we are to evaluate the indefinite integral of dx over 6x plus 1. And we can't let x be minus 1/6, because if x is minus 1/6, this won't be continuous, and our fundamental theorems of calculus don't work. Now, our choice then is going to be, in this case, we're going to let u equal 6x plus 1. That means du is equal to 6 dx. And here, you see, this is the first one we're doing that's not perfectly clean. Dx then is going to be, I divide both sides by 6, it is du over 6. So you see, I go over here and I'm going to be doing my substitution. This is just u, but then dx is du over 6. So this is du over 6. Now I'm going to pull that 1/6 out of the integral sign outside. And so this is 1/6 the indefinite integral of du over u. Well, this integral is known to be the natural logarithm of the absolute value of u. So it's 1/6 that, and I add a c for the constant of integration. And then I reverse my substitution and get this as an answer. The absolute values are important in this case because 6x plus 1 can be negative or positive. And example 8 is different because we're actually doing a definite integral. So you see, whereas we were always getting families of functions before, the answer to this problem is going to be a number. And the example says round to the nearest thousands. Okay, so let's just get started on this, but I'm going to tell you at the outset the answer is going to be a number, and you must be mindful of your limits, and we'll talk about that. So we're just going to consider the antiderivative to start with. And so we have this, and we can pull the 5 out, which I do here, but now I'm going to make a choice for my substitution. And my choice for my substitution is going to be, and notice that I have the square root of x squared plus 3, and then I have an x dx. So what I'm going to do is I'm going to let u equal x squared plus 3. I don't know if that's going to work yet, but we'll see if it does. And du, in this case, is equal to 2x dx. So let's see if we can substitute that. So you see, what happens is, then I have, this is the square root of u, and du was 2x dx, and that means that dx is du over 2x. So if you think about that, magic happens, because dx is du over 2x. So the x's cancel. That's magic happening. And so what we have at the end of that substitution is 5, the square root of u, du over 2. We pull that out. That makes it 5 over 2 in front. And what is left is u to the 1/2 du. We can integrate this. So now the 5 over 2 stays out there, but now we add 1 to the exponent, divide by the new exponent, and what we see is u to the 2/3 times 2/3. If you divide by 3/2, you get 2/3 plus c, and so I multiply those things together. And let's see, the 2's will cancel. That's 5 over 3, and it's x squared plus 3 to the 3/2 plus c. But now we have to evaluate this as a definite integral. Again, you can take c to be 0 when you're evaluating the definite integral, and so what we're doing is we're writing that. But here's the important part. As I say, you have to be mindful of the limits. If what you write here has x's in it, then your limits have to be the x's. If what you write here has u's in it, your limits would have to be u's. But now we just use the fundamental theorem of calculus. We put the top limit in, subtract what we get when we put the bottom limit in. We do the algebra, and we get to this. Now, some of my students will say, Jim, that's really an ugly number, but there are no ugly numbers, just like there are no ugly babies. And so this is the exact answer, and if you were in my engineering calculus class and it was a non-COVID time, I would expect you to give me this as the answer. But you can also plug that into a calculator and find out that's approximately equal to 4.673, and that should be an approximately equal to symbol. Be mindful of your limits. Here's another example. Now this one is called evaluating. Again, it's back to an indefinite integral, and it is x divided by x plus 2 dx, and we're assuming that x is bigger than minus 2 because we don't want to deal with the 0 in the denominator here. Okay, now this is a little bit of a double substitution, and a way to do with this is to say, let's let u equal x plus 2, but if u equals x plus 2, then x is equal to u minus 2, and du and dx are the same with this substitution. So we're going to do that substitution here then. So this is going to be u minus, so here's the original problem. We will do that substitution, so this is going to be u minus 2 over u du. And now I'm going to divide this u. Now I'm doing algebra, not calculus. I'm dividing this u into both of those terms. So u goes into u one time, and u goes into 2 over u times. So this is the same as 1 minus 2 over u times du. So I'm going to integrate term by term. Add 1 to the exponent, divide by the new exponent, that is just u. Here, pull out the minus 2, that's 1 over u. And the indefinite integral formula for that is natural logarithm of u. And then we have plus a constant. But now we're going to reverse our substitution. U is equal to x plus 2. So this x plus 2 right here is from that u. And then I put x plus 2 in here. And technically, I think I would have put the absolute value of x plus 2, but these notes did not, plus c1. And now we observe that if this is a constant c1 and this is 2, then you can put those two together and just call it c equals c1 plus c2. And here is a final answer once I've reversed my substitution. And again, I would have put the absolute values there probably. In summary, integration by substitution anticipates application of the chain rule where an antiderivative is differentiated. Substitutions must be reversed after the integration has been performed so that the original variables appear in the solution. This is when it's an indefinite integral. When it's a definite integral, the answer will be a number, and you could do it either way. But you must be mindful of the limits when you're doing those integrals. If your antiderivative you're evaluating is in terms of u, your limits must be u. If the expression that you're evaluating has x's in it, your limits must be x. And all antiderivatives can be checked using differentiation. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.